All right, let's talk about something that powers, well, basically our entire modern world, electricity. We're going to crack the code on this thing, strip it down to the absolute basics, and make it super easy to understand. Ready? Let's jump in.
So how are we going to do that? We're going to use one simple but really powerful idea. Just imagine for a second that electricity moving through a wire is exactly like water flowing through a pipe. If you can keep that picture in your head, everything else is going to click into place.
Here's the game plan. We'll start with the absolute basics. What is flow? Then we'll look at the forces that control that flow. After that, we'll get into the one rule that ties it all together, look at a couple of ways you can set things up, and wrap it all up with why things get hot.
Okay, first up, what is electric current really? I mean, what is actually moving inside that wire to make our stuff work?
So, the official definition is that electric current is the flow of electric charges. And these charges are tiny, tiny particles called electrons. When they move through something like a metal wire, which we call a conductor, that's it. That's electric current. It's really just electrons on the move. And here's where our water analogy just works perfectly. You know how a water current is just a bunch of water molecules flowing together in a river? Well, an electric current is the exact same idea. It's just a stream of electrons flowing together in a wire.
But here's the catch. For those electrons to actually go anywhere, they need a complete path, and we call that an electric circuit. It has to be a continuous, unbroken loop. If you cut the wire, or even just open a switch, it's like putting a cap on a pipe. Everything just stops. No closed path means no current. Simple as that.
Okay, so we've got a flow, but what makes it flow in the first place? And what could slow it down? That brings us to two really important new ideas, what I like to call the push and the squeeze.
First, let's talk about the push. In electricity, this push is called voltage. You can think of it as electric pressure. It's the force that gets those electrons up and moving. Without voltage, the electrons would just be sitting around, totally calm, like water in a perfectly flat pipe.
So if voltage is the push, what actually does the pushing? A battery. A battery is basically the water pump of the electrical world. You know, a pump creates water pressure to shove water through pipes, while a battery creates that electric pressure, the voltage, to push electrons through a circuit.
Now, let's talk about the squeeze. See, as those electrons are flowing, they don't exactly get a free ride. They're constantly bumping into the atoms inside the wire, and that creates a kind of friction. This opposition, this thing that slows down the flow, is called resistance.
And our analogy holds up great here too. Electrical resistance is just like a really narrow section of pipe. It literally squeezes the flow, which makes it way harder for the water, or in our case, the electrons, to push their way through.
So what makes something have more or less resistance? It comes down to three main things. First, the length. A longer wire has more resistance. It's like a longer obstacle course for the electrons. Second, thickness. A thicker wire has less resistance because there's just more room to flow. And finally, the material itself is a huge deal. Copper is like a superhighway, while other materials are more like a narrow, bumpy road.
So, now we've got our three big ideas. Current, which is the flow, voltage, which is the push, and resistance, the squeeze. And it turns out there's a really simple, elegant rule that connects all three of them. It's called Ohm's law, and it's kind of electricity's golden rule.
And there it is, V equals I times R. Or, if we put it back into our easy analogy, the amount of push you have is just the rate of flow multiplied by the amount of squeeze. The big takeaway here is that these three things are always connected. You can't change one without affecting the others.
Let's think about that for a second. Let's say you keep the squeeze the same, right? But you increase the push. Maybe you use a stronger battery. What happens? Well, the flow of electrons speeds up. The current gets stronger. Now, what if you keep the push the same, but you increase the squeeze by using a more resistive wire? The flow of electrons slows right down. The current decreases. It's a perfect balancing act every single time.
Okay, so we've got the rules of the road. Now let's see how we can actually build stuff with them. Turns out, there are two basic ways to wire things up. You can give the current only one path to follow, or you can give it options.
A series circuit is the simple one. Everything is connected in one long line, one after another. This means the current has to go through every single component, no exceptions. But in a parallel circuit, the path actually splits. The current divides up, flows through different branches at the same time, and then comes back together at the end.
So why should you care about this? Well, think about those old cheap holiday lights. They were wired in series. And if one tiny bulb burned out, it broke that single path and the entire string went dark. Ugh, what a nightmare. That's exactly why your house is wired in parallel. You can turn off a lamp in one room and your TV in the other room keeps on working because its current has its own separate path to follow.
All right, for our last section, let's talk about a super useful side effect of all this. Remember that friction we talked about? The electrons bumping into atoms as they flow? Well, that doesn't just slow things down. It also creates heat.
This is called the heating effect of electric current. And yeah, sometimes it's an annoying waste of energy, but we have figured out how to harness it. That heat is exactly how an electric toaster works, or a space heater, or a clothes iron. We actually choose materials with high resistance just so we can create a bunch of heat when we want to. Pretty clever, right?
And when you look at the numbers, the differences are just staggering. Look at copper. It has an insanely low resistance, which is why we use it for wires. We want the electricity to flow easily. But then look at nichrome, the stuff in heating elements. It's almost 100 times more resistive. And something like glass, its resistance is so astronomically high, it basically just stops the current cold.
This idea gets taken to a wild extreme in an old-school incandescent light bulb. The little filament inside is made of tungsten. Why? Because tungsten can get white hot, literally thousands of degrees, and glow like crazy without just melting into a puddle. We're using that heating effect to literally create light.
So there you have it. Electricity isn't some invisible magic. At the end of the day, it's just a flow. And that flow is controlled by a push and a squeeze, all following a few simple rules. From the phone in your pocket to the lights in your room, it's all just electrons on a very, very carefully planned trip.